The final concept we are going to discuss this week is functional completeness. Now, this is related to a set of logical operators. Well, we did not really talk about what a set is, but I will trust that you have a notion of what a set is. It's essentially a collection. So consider logical operators like AND, OR, negation, XOR, implication, biconditional, etc. Whatever operators you can think of. And consider a set consisting of some of those, right? For instance, this one. This is a set of operators, and its elements are AND, OR, and negation. Now, such a set of logical operators is called functionally complete if all possible truth values, or rather, all possible truth tables, logical functions, in other words, can be expressed in the given set of operators. Now, what does this mean? Suppose you are dealing with, let's say, 3 logical variables, okay? Let's say P1, P2, P3. And as we have discussed, you can have 2 to the power 3, 8 distinct input combinations, which means 2 to the power 8, in total 256 possible distinct functions. Okay, so take any set of logical operators. Is it possible that using only those operators in that set, can I express all of those 256 functions? That is the question. If the answer is yes, we say that that set of logical operators is functionally complete, meaning it's complete in the sense that it can express all propositional functions possible. Okay, and this just 3 logical variables is just an example. We are talking about all possible logical functions, irrespective of the number of logical variables. Now, our discussion on conjunctive and disjunctive normal forms demonstrate that this function, set of logical operators is functionally complete, because whichever logical function you can give me, using the procedure we described using min terms and max terms, etc., depending on how many inputs it accepts, I can always find a conjunctive normal form and a disjunctive normal form to represent that function, which means, well, recall the min terms are made up of ANDs and negations, and they are combined using ORs. And on the other hand, the max terms consist of operations ORs and negations, and we combine them using ANDs. You see, these are the only operators we need to represent any propositional function you can think of, which means this set is functionally complete. Okay, which means using these 3 operators, I can express any propositional function that you will give me. So this set is functionally complete. The question is, are there others? Are there other set of logical operators that are functionally complete? Especially, are there smaller ones? Because, well, in mathematics, we like to have simple answers. And for instance, if you add something to this, and or negation, and let's say implication, this set of logical operations is also functionally complete, because I don't even need this. I can express anything using these, so this is definitely functionally complete. But can I go the other way around? Can I make this set smaller? Now, observe the following. I can express P or Q as the negation of not P and not Q. This follows from the Morgan's laws, therefore it's not that difficult to see. But you see, the significance of this is it eliminates the necessity of OR. because I can express or in terms of negation and. Therefore, whatever I can express using or and negation, any or I have using this, I can replace it with ands and negations. Therefore, any expression involving or can be transformed into an expression without or, but just involving and negation, which means this set consisting of only and negation is also functionally complete. And it's a smaller set than this one. So that's a good answer. And you can also go the other way around, because you see, I have that, but I also have this. And can also be expressed in terms of or and negation, which also means by the same argumentation, this set is functionally complete. Right. Now, at this point, I have functionally complete sets consisting of just two operations. Or and negation is sufficient. At the same time, and negation is also sufficient. Can I go one step further? Is there a single operator such that using that single operator only, I can express all possible propositional functions? And the answer is actually yes. Now, observe this. Now, what is this? First of all, let's recall this from this set of possible binary operators. And you see, it's defined here. The NAND operation is defined as the negation of P and Q. So going back to this discussion here, if you NAND a proposition with itself, you get the negation of that proposition, because this essentially is by definition equivalent to P and P negated, and P and P is just P, because if P is true, P and P is true, and if P is false, P and P is false. And when you negate it, what you get is, according to De Morgan's law, not P or not P, and that is essentially equivalent to not P. So if you negate if you NAND a proposition with itself, you get its negation. So NAND can provide negation by itself. On the other hand, AND, for instance, can be obtained using NAND. Why? Because NAND already by definition is the negation of and therefore to obtain AND, I need to negate it once more. So if you negate P NAND Q, you will get just P and Q. And to negate it, I have just seen that NANDing with itself negates the proposition. Therefore, I am going to NAND this with itself to obtain P and Q. So what does this mean? I know that this is functionally complete, the set consisting of and negation. But I have just seen that for negation, I can use NAND. And for and, I can also use NAND. So I can use NAND to represent any negation and any AND operation. Therefore, NAND by itself is functionally complete, right? It's just a single operator, but it happens to be sufficient to represent any propositional function you can give me. In a very similar way, you can prove that NOR has the same property. Now, as I said, from a mathematical point of view, simplification is always good. But from an engineering point of view, is there a practical result or a practical application of this? And the answer is yes. And this is significant in digital electronics. Why? because NAND gates are relatively smaller in number of transistors and silicon area, and designs with NAND logic procedure produce smaller circuits with smaller delays because it requires fewer number of transistors. It takes smaller areas, which means the delay you are going to get from your digital circuit is going to be smaller. And also it's going to be in a smaller silicon area, which means it's going to be cheaper because it will require less amount of material. And furthermore, it's going to heat up less. Therefore, these are all advantages using NAND logic, and it's a practical application of a mathematical result to a real-world engineering application.